As the switch S is closed in the circuit shown in the figure, then the current passed through the circuit is. What will be the current through this path? That's the question asked. If switch S is closed, what will be the current through the path? So, question number 19. This is A, which is 20 volt, and this one is 5 volt, which is B. This is 2 ohm, this one is 4 ohm. This is the ground. The switch is this is 2 ohm. Let us assume the potential at this particular point is V. Here, if the switch S is closed, what is the current through this path? That's the question. As we look at the diagram, we can understand that this is a junction where all the three conductors meet. So we are going to apply Kirchhoff's current law, or else you can say junction law. The algebraic sum of the currents meeting at any junction in the circuit is 0. I can say I1 be the current flowing towards this junction, and I2 be the current flowing towards the junction, and I3 be the current flows away from the junction, because this is positive potential, this is positive potential. So current tends to flow through this path, and they meet at the junction and they move out as I3. So I3 equals I1 plus I2. What we need is I3. We need to calculate I3. So I can write I3 is I1 plus I2. I3 is I1 plus I2. Current is voltage divided by resistance. Potential difference divided by resistance. For this particular resistor 2 ohm, I can write I1 is 20 minus of V divided by 2 plus I2 is 5 minus of V divided by 4. This is equal to V minus of ground has a 0 potential. So V minus of 0 divided by 2. Multiply by 4 on both sides. We will have 2 into V equals 2 into 20 minus V plus 5 minus V. 40 minus of 2V plus 5 minus of V equals 2V. Minus 2V minus V minus 3V. As it comes this side, we will have 5V. This is equal to 45. V equals 45 divided by 5, which is 9 volt. So at this point, potential is 9 volt. Potential is 9 volt. We are asked to calculate the value of current. I3 is equal to V divided by R. V minus 0 divided by R. V is 9 volt minus of 0 divided by 2 ohm. So 9 by 2 is 4.5 ampere. The current through this path is 4.5 ampere. Option is A. Now, 20th question. The battery is charged at a potential of 15 volt for 8 hours when the current flowing is 10 ampere. The battery on discharge supplies a current of 5 ampere for 15 hours. The mean terminal voltage during discharge is 14 volt. The watt-hour efficiency of the batteries. So we are speaking about the charging and discharging process of a battery. They are asking to calculate the watt-hour efficiency. Question number 20. Watt-hour efficiency is equal to the ratio of discharging energy divided by charging energy. Discharging energy by charging energy. Energy is nothing but power into time. So VIT at the time of discharge divided by VIT at the time of charging. Potential at the time of discharge is given 14 volt. Current 5 ampere. Time 15 hours. Divided by potential during charging is 15 volt. Current is 10 ampere and time is 8 hours. Let us simplify. We cancel this. This is 2 and this is 7. So 7 by 8. This is watt-hour efficiency. Efficiency must be calculate it in terms of percentage. To get percentage, multiply with 100%. So this will be 12.5. 7 and 12.5, 87.5%. So water efficiency is 87.5%. D option. D option. Now, question number 21. A wire of certain material is stretched slowly by 10%. It is given stretched slowly by 10%. Its new resistance and specific resistance will become respectively. They are speaking about new resistance and specific resistance. So when you say a wire is said to be stretched, then what will happen? Length increases, correspondingly area will decrease and the resistance increases by n square times. So based on that idea, we are going to calculate the value of new resistance and specific resistance here. It is question number 21. It is given length is increased by 10%. Already length L is there. It is stretched by n% or 10% of L. So L plus 10 by 100 of L. 10 by 100 is 1 by 10, which is 0.1. So L plus 0.1 L. 1.1 L is the new length. What will be the value of area? A prime will be A divided by 1.1. What will be the value of new resistance? Rho L prime divided by A prime, which is rho into 1.1 L divided by A divided by 1.1. So rho L divided by A into 1.1 the whole square. 1.21 into R. So R prime is 1.21 into R. So it increases, resistance increases by 1.21 times. What will happen to specific resistance? Always remains constant. Always remains constant. So the option is it increases by 1.21 times, resistance increases by 1.21 times, and specific resistance remains the same. Then question number 22. A current of 3 ampere flows through 2 ohm as shown in the circuit. The power dissipation in 5 ohm resistors. A current is flowing through 3 ampere is flowing through 2 ohm. What is the power dissipation across 5 ohm resistor? You can check it out. Circuit is given. Instead of giving potential, they have given the value of current. 3 ampere current is flowing through 2 ohm resistor. This is 4 ohm. This is 1 ohm and 5 ohm. They are asking you to calculate the power dissipated across 5 ohm resistor. Now, what is the potential across this path? As you know the value of current and the resistance, we can write V equals IR. So 3 into 2, 6 volt. If potential across this 2 ohm is 6 volt, then potential across 4 ohm is 6 volt, potential across 1 ohm, 5 ohm is also 6 volt, because this is a parallel connection. In a parallel combination, the resistances means potentials are the same. So we can say the potential across 4 ohm is 6 volt, potential across this combination is also 6 volt. All the potentials are 6 volt. Our intention is to calculate the power dissipated across 5 ohm resistor. So we need to know the value of current flowing through this path. So current I equals V divided by R, potential is 6 volt, total resistance 5 and 1 are in series, so 5 plus 1, so 6 by 6, 1 ampere. As 1 ampere current flows through this path, we can say the potential drop across 1 ohm is I into R, which is 1 into 1, 1 volt. Potential across 5 volt is I into R, once again, this is equal to 1 into 5, this is 5 volt. So potential drop across 5 ohm is 5 volt. What is the power dissipated? P equals V square divided by R. 5 into 5 divided by 5, this gets cancels out, so 5 watt. The power dissipated across 5 ohm resistor is 5 watt. Option D. Option D. Idea is very simple. If one potential is potential across any one of the paths is known, for the parallel combination, the potentials are of the same value. Keeping that potential, we can simply calculate the idea here. And what will be the potential power dissipated across 4 ohm resistor? We can simply calculate. P equals V square divided by R. Potential is 6, so 6 into 6 divided by resistance is 4 ohm. So this is 3, this is 2, and this one is 3. 9 watt. 9 watt. It is the power dissipated across 4 ohm resistance. So if potential is known, we can easily calculate what the power dissipated across any resistor. Now, question number 23. See the electrical circuit shown in the figure. Which of the following equation is correct for it? Once again, we have to go for Kirchhoff's loop rule or otherwise Kirchhoff's voltage rule. Right? In a closed path, they are asking you which of the following expression is correct. You draw the diagram for this question. A resistor, a battery, so this is capital R, EMF is E1, this is R1, current is I1, current here is I2, this is R2, and this is E2. These two currents add up and will become I1 plus I2 along this path, through this path. So here the current flows as I1 plus I2. They are asking you which of the following expression is correct. I can take this path A, B, C, D. I am applying Kirchhoff's voltage law to the closed path A, B, C, D. Kirchhoff's voltage law to the closed path A, B, C, D. So I am just going from this point. As I am taking a travel along the direction of flow of current, I can take minus of I1 plus I2, product of current and the resistance, I1 plus I2 into R. As I go through this path, I am going along the direction of flow of current, so minus of the current through this path is I1, so I1 into R1. As I move from low potential to high potential, it is positive, so plus E1, this is equal to 0. So expression will be E1 minus of I1 plus I2 into R minus of I1 R1 is equal to 0. First option. First option. So you are applying Kirchhoff's voltage law here. Here, in this particular path, the current is I1 plus I2. So through resistor capital R, current flow is I1 plus I2. Product of current and resistance is taken negative because direction of travel is along the direction of flow of current. So minus of I1 plus I2 into R. As I go through this path, current is I1 and direction of travel is along the direction of current. So minus of I1 R1 plus low potential to high potential positive E1. This is equal to 0. So on rearranging this expression, I will get first option. In the circuit shown in the figure, if potential at point A is taken to be 0, this point is 0 potential, the point potential at point B is right. We have to apply Kirchhoff's voltage law here for this circuit diagram also. Question number 24. I can take the path from A to B alone because all the other paths are not required. As we are speaking about Kirchhoff's voltage law, we can take any of the closed path. If we are given two potential points A and B, I can go along this path alone from A to C, then to D, and then to B. So I can reconstruct the circuit like this. It is VA, and then a potential, and this point is C. Before going to this, I would like to mention the current flowing through this path. If you look at this particular junction, 2 ampere current is moving out of this junction. 1 ampere current is flowing towards the junction. Then obviously 1 ampere current must flow through this path. 1 ampere current must flow through this path. If 1 ampere current and 1 ampere current are flowing towards the junction, then the 2 ampere current will flow away from the junction. So Kirchhoff's first law is said to be satisfied. So the current through this path DC is 1 ampere. So I can draw the circuit in this form. This is C. From C to D, 1 ampere current is flowing, and then from D Another cell is, or battery is given with a 2 volt potential. This is VB. So this is the route by which we are going to apply, route through which we are going to apply Kirchhoff's voltage law. So VA is the potential. As I am going along this direction, let us say 1 ampere current is flowing through this path, 1 ampere current is flowing through this path. We can say VA, then low potential to high potential, so it is positive plus 1, and this is the direction of travel where the current is in the opposite direction, so this is positive. 1 into 2 ohm is 2, so product of current and resistance is 2 volt, so it is 2. Then as I go from this point to VB, high potential to low potential, so negative minus 2, this is equal to VB. So minus 2 plus 2 cancels out, VA is given 0 potential, so VB equals plus 1 volt. VB equals plus 1 volt. So as we see in the diagram itself, we can see here I am going along this path and reaching B. So as I am moving along this path, low potential to high potential, so positive 1 volt, VA is 0 volt. As I am going in a direction opposite to the current direction, this is plus 2 volt, and here high potential to low potential minus 2 volt, potential at point VB is required. So plus 1 volt, plus 2 volt, minus 2 volt, minus 2 plus 2 cancels out, VB equals plus 1 volt. Then question number 25. A ring is made up of a wire having a resistance RO equals 12 ohm. Find the points A and B as shown in the figure. Find the resistance between the points Find the resistance between the points A and B as shown in the figure, at which a current carrying conductor should be connected so that the resistance R of the sub-circuit between these points is equal to 8 by 3. Actually, what is asked? A ring is as shown. The total resistance of the circuit is given 12 ohm. Total resistance is 12 ohm. And if you calculate the effective resistance between A and B, if you replace this smaller portion of the wire and the larger portion of the wire by a single wire, then its effective value is equal to 8 by 3 ohm. Is equal to 8 by 3 ohm. Then they are asking you to calculate the ratio of L1 by L2. What will be the ratio of L1 by L2? Idea is very simple. This L1 and L2 are said to be in a parallel combination. We have to calculate what is the value of ratio of L1 by L2. In order to calculate L1 by L2, we need to know the value of R1 and R2. We shall go by this way. Question number 25. A ring is given. These are the 2 points A and B. L1 and L2 are the lengths. The total resistance RO equals, if I consider this as R1 and this one as R2, before taking these 2 points A and B, this is a complete ring. So if you start from this point, this is a complete ring. So R1 and R2 are considered to be in series. So RO equals R1 plus R2 equals 12 ohm. That's the meaning. RO equals R1 plus R2 is equal to 12 ohm. This is what is mentioned. Actually, before these 2 points A and B are chosen, are selected, this complete wire has some resistance. This is equal to a lengthy wire which is made into a circle. So RO equals R1 plus R2. This is the meaning. These two are supposed to be in series. So RO equals R1 plus R2, which is 12 ohm. When 2 points A and B are chosen on this circular ring, then this 2 comes in parallel. R1 and R2 comes in parallel. Right? Because A is a common potential point for these 2 ends and B is the common potential for these 2 ends. So these 2 are in parallel. And they have given the effective resistance Rp is equal to 8 by 3 ohm. Effective resistance Rp equals 8 by 3 ohm. Now, we can start solving this question. Rp equals, as you know, R1 R2 divided by R1 plus R2. Rp is 8 by 3. R1 R2 divided by R1 plus R2 is given 12 ohm. So from which we can calculate R1 R2, which is 8 by 3 into 12, 4, 32 ohm. So R1 R2, product of R1 and R2 is 32 ohm. Now we can write R2 minus of R1 the whole square, because as you know, if length is more, resistance is more, length is less, resistance is less. R is proportional to L. R is proportional to L. If length is more, resistance is more. If length is less, resistance is less. So greater resistance minus lesser resistance. R2 minus of R1 square is equal to R2 plus R1 the whole square minus of 4R1 R2. R2 plus R1 the whole square is given 12 ohm. So 12 square minus of 4 into R1 R2. The value of R1 R2 is 32 ohm. So you can substitute 32 here. 144 minus of 128, this is equal to 16. R2 minus of R1 the whole square equals 16 ohm. R2 minus of R1 is 4 ohm. As we know, R2 plus R1 is 12 and R2 minus of R1 is 4. We can calculate 2R2 is equal to 16, R2 equals 8 ohm. If R2 equals 8 ohm, R1 is equal to 4 ohm. We can substitute in any of the equation. R1 is equal to 4 ohm. So they are asking you the ratio. R1 by R2 is equal to L1 divided by L2, because R is proportional to L. R1 by R2 equals L1 by L2, which is 4 divided by 8, which is 1 divided by 2. So L1 by L2 ratio is 1 by 2. First option. L1 by L2 ratio is 1 by 2. Now, two cities are 150 km apart. Electric power is sent from one city to another city through copper wires. The fall in the potential per kilometer is 8 volt. Fall in the potential per kilometer is 8 volt. And the average resistance per kilometer, look at the statement, this is for per kilometer, is 0.5 volt. The power loss in the wires, they are asking you to calculate the power loss. Two cities are 150 km apart. You take this, AB, 150 km apart. 150 km apart. The resistance per kilometer, this is 1 kilometer. The potential drop per kilometer is 8 volt. Potential drop per kilometer is 8 volt. And the resistance per kilometer is 0.5 ohm. Resistance per kilometer is 0.5 ohm. Then what is the power loss in the wire? In order to calculate the power loss, we need total potential square divided by total resistance. We are given potential drop per kilometer, resistance per kilometer. For 1 kilometer, the potential drop is 8 volt. So for 150 kilometer, potential drop is 8 into 150. So 1200 volt. Similarly, resistance per kilometer is 0.5 ohm. Resistance for 150 kilometer is 0.5 into 150 is equal to 75 ohm. Now power loss can be calculated. V square divided by R. 1200 into 1200 divided by 75. When you simplify this, you will get 19,200 watt, which is 19.2 kilowatt. This is the value of power loss. So power loss is 19.2 kilowatt, option B. Finally, question number 27. Two metal wires of identical dimensions are connected in series. If sigma 1 and sigma 2 are the conductivities of the metal wires respectively, the effective conductivity of the combinations. Two wires of conductivities, sigma 1 and sigma 2, but they are all identical dimensions. So I can consider L1 be the length of one wire and L2 be the length of another wire. Since they are mentioned as same dimensions, L1 equals 1, L2 equals 1, area of cross section for the entire wire is same, and they are speaking about conductivity sigma 1 and sigma 2. They are asking you to calculate the effective conductivity. So for effective conductivity, effective resistance can be taken as R equals rho L divided by A as reciprocal of resistivity is conductivity, we can write this as L divided by sigma A. As we are calculating effective value, R effective equals L divided by sigma effective into A. As the two conductors are connected in series, I can write R effective is equal to R1 plus R2. So L divided by sigma effective A equals L divided by sigma 1 into A plus L divided by sigma 2 into A. L by A is cancelled on both the sides. Actually, while taking this length L, actually this L and L are same, but here the total length, when effective value is to be calculated, total length is 2L. Total length of the conductor is 2L. Area of cross section is the same. And the two conductors are connected in series, effective length is 2L. So L prime must be replaced as 2L divided by sigma effective into A is equal to L divided by sigma 1A plus L divided by sigma 2A. This L by A, L by A, L by A gets cancels out. 2 divided by sigma effective is equal to sigma 1 plus sigma 2 divided by sigma 1 sigma 2. On cross multiplying this, sigma effective is equal to 2 sigma 1 sigma 2 divided by sigma 1 plus sigma 2. This is the effective value. Sigma of 2 sigma 1 sigma 2 divided by sigma 1 plus sigma 2. Effective value of conductivity of the combination is B. We are going to speak about the delta to star connection and star to delta connection. When three resistors are connected in the form of a triangle, in order to simplify the circuit diagram, we can go from delta to star connection. And if the circuit is in the form of a star, then you can convert it into delta connection. If three resistors are connected in the form of a triangle, which forms a star connection, let us say, that means delta connection ABC, this can be converted into a star connection, X, Y, Z. Let us mark this as R1, R2, R3. So this delta can be transformed to a star connection. This is A, B, C, X, Y, Z. What will be the, how will you convert this delta to star? What will be the value of X? If you want to calculate X, this is equal to the product of the resistances which are on either side of X, which is R1, R2, divided by total resistance of the circuit, R1 plus R2 plus R3. So I can write R1, R2 divided by sum over R. So X can be calculated. And in the same way, if R2 and R3 or Y has to be calculated, the value of Y can be found by taking the product of these two resistances R2 and R3 divided by sum of the resistances R1 plus R2 plus R3, which is R2 R3 by sum over R. Z can be calculated with these two resistances, which is R1 divided by R1 plus R2 plus R3. This is equal to R3 R1 divided by sum over R. What is the need of this circuit? If suppose a balanced Wheatstone network is given, you can easily simplify the circuit and you can give out the answer. If an unbalanced Wheatstone network is given, then how will you calculate the effective resistance of a given circuit? There, you have to go with this delta to star connection and star to delta connection. This is delta to star. What about star to delta connection? This is A, B, C, X, Y, and Z. Or otherwise, this is R1, R2, R3. This delta must be converted into star. X, Y, Z. X, Y, and Z. How will you calculate or how will you find out the value of the star to delta? So we have to transform this into a delta circuit. A, B, C, X, Y, Z. How this star connection will get transformed to delta connection? How will you find out the value of X? Here, X is equal to sum of these two resistances, which is opposite to this X, R1 R2. So R1 plus R2 plus of product of the same resistance R1 R2 divided by the remaining resistance R3. You just look at the case here. The two resistances which are forming the other two sides of the triangle of this one is x equals R1 plus R2. These two triangles are in this triangle. The two resistances are there. R1 and R2 are there. You sum up the two resistances R1 plus R2 plus product of the two resistance R1 R2 divided by R3. In the same way, for y, you can write two resistances are R2 and R3. So I can write R2 plus R3 plus R2 R3 divided by the opposite resistance, which is R1. And Z is equal to two resistances R1 R3. So R1 plus R3 plus R1 R3 divided by R2. So yes, the delta connection can be transformed to star connection and the star connection can be transformed to delta connection in order to simplify the given electrical circuits. If you look at this particular diagram, this circuit is not a balanced Wheatstone network. How will you solve this unbalanced Wheatstone network? Here we can apply this delta to star connection, star to delta connection. Here, this arrangement is similar to that of a delta connection. This can be transformed to a star connection, let us say x, y and z. So, to find out x, we already saw the formula. It is the product of these two resistance divided by the sum of all the three resistances. You just leave this portion of this circuit. We are considering only this circuit. This forms a delta connection. In this delta connection, I need to calculate the value of x. X equals, if I write this as R1, R2 and R3, all the three resistances are 3 ohm each. To find out x, it is the product of the resistance on either side of x. So 3 into 3 divided by, or I can use the formula here, R1 plus R2 divided by sum over R. R1 into R2 is 3 into 3. Divided by all the three resistance are taken as sum, which is equal to 9. 9 by 9 is 1 ohm. Similarly, y is equal to 3 into 3 divided by 9, which is 1 ohm. Z equals 3 into 3 by 9, which is 1 ohm. So this circuit can be reconstructed to this one, x, and then another resistance, and then this 2 ohm and this 5 ohm. The circuit got reduced to this one. This is x, this is y, this is z, and this is 2 ohm already given. This one is 5 ohm given. So the value of y is 1 ohm, value of z is 1 ohm, value of x is also 1 ohm. Now we can simplify the circuit easily. This 1 ohm and 2 ohm are in series. So 1 ohm and 2 ohm are in series. This 1 ohm and 5 ohm are in series, effective are in parallel. This is 1 ohm, 2 ohm, 1 ohm and 5 ohm. 1 and 2 are in series, effective value is 3 ohm. This is 6 ohm and this one is 1 ohm. 6 ohm and 3 ohm are in parallel. So 6 into 3 divided by 6 plus 3, 18 by 9, 2 ohm. So circuit will be 1 ohm and 2 ohm. So between A and B, the effective resistance is, or AB is 2 plus 1, 3 ohm. Effective resistance is 3 ohm. So the simple way by which you can calculate the effective resistance of an unbalanced Wheatstone network. If not, you have to go for Kirchhoff's current law and voltage law, and then you have to simplify. That is too hectic. For star to delta connection, actually this is a star connection. I can transform this to a delta connection. Already there is a delta existing. Inside there is a star connection. I am transforming this star connection into delta connection, which is shown in the black dotted line. I can mark this as, let us say, R1, R2, R3. This side is taken X, this one is Y, and this one is Z. You have to find out the value of x, y and z. X is equal to R1 plus R2, formula is this one, R1 plus R2 plus R1, R2 divided by R3. What is R1? 6 ohm, R2 3 ohm plus R1, R2 6 into 3 divided by R3 is 4. So 9 plus 18 divided by 4, 36 plus 18 divided by 4, which is 54 divided by 4. X is 54 by 4 ohm. And then to calculate y equals R2 plus R3 plus R2 R3 divided by R1. R2 is 3 ohm, R3 is 4 ohm, 3 into 4 divided by R1 is 6 ohm. So 7 plus 12 divided by 6, 42 plus 12, 54 divided by 6, 9 ohm. So y equals 9 ohm. And what about the value of Z? To find out Z, the resistances are, they are on the other sides of the triangle are R1, R2 plus R1, R2 divided by R3. R1 is 6 ohm, R2 is 4 ohm plus 6 into 4 divided by 3. So 10 plus 24 divided by 3. 30 plus 24 by 3, which is 54 by 3, 18 ohm. So Z is 18 ohm. So this circuit can now be reconstructed like this. Already there is a delta connection. A star is transformed to delta. Can make this as A, B, C. This is 9 ohm already. This is 54 by 5 ohm already. And this is 18 ohm. Now this got transformed to another star connection. And this is not the one. Star is transformed to delta. The value of X is 54 by 4 ohm. And the value of Y is 9 ohm. And value of Z is 18 ohm. So the star connection has been transformed to delta connection in this way. Now it is very simple. 54 by 5 and 54 by 5. The resistances between these two points B and C are in parallel. Between A and B, these two resistors are in parallel. Between A and B and between A and C, these two resistors are in parallel. So these resistances are in parallel. These ones are in parallel, and these resistances are in parallel. We have to find out the effective value. Effective resistance between C and B is 54 by 5 into 54 divided by 4, R1 R2 by R1 plus R2. 54 by 5 plus 54 divided by 4. So we will have 2916 divided by 20 divided by 20. 6 plus 250. So this 20 will get. So this will be 1. So on simplifying this entire value, you will get RCB is equal to 6 ohm. The same way, RAB is equal to 9 into 18 divided by 9 plus 18, which is 6 ohm. Between R and RAC, this is 9 into 18 divided by 9 plus 18. This is also 6 ohm. So the entire circuit reduces to an arrangement as shown. A, B, C, 6 ohm, 6 ohm and 6 ohm each. Now AC and CB are in series and their effective is in parallel. 6 plus 6, 12. So this circuit reduces to 6 ohm and this one is 12 ohm. This is AB. 6 and 12 are in parallel. RP is equal to 6 into 12 divided by 6 plus 12. So 72 divided by 18. That's all. The effective resistance across AB is 4 ohm. This is how star to delta connection is used. Actually, if you look at this expression, look at this circuit, solving this circuit is more complicated. If you use the star to delta connection, it will be very simple. That's all. Thank you.